I'm going to show you one more example of a prop, which is the prop that says that a regular expression matches a string. So I'm going to write, here I've got lists, concatenation, and the data type for regular expressions. And I'm going to write prop match string x, where, and now I need to list all of the ways in which a regular expression can match a string. So the first case is, the first thing that a regular expression can be is an atom, a single letter. So I'm going to say, I can prove that atom x matches. So I would like to say that this matches the string x cons empty by letter. But remember, I still have this restriction that each letter can appear only once. So instead, I have to say that atom x can match y cons empty, but then I have to prove as a sub-goal that x equals y. Okay, so the next thing that a regular expression can be is the zero regular expression, but this doesn't match any strings. So I'm not going to have any proof rules for it. I don't want to have any way to prove that zero matches something. So the next thing after that is I, and this matches the empty string. So I'm going to say, I can prove that I matches empty, and I'm going to say by done. All of these names are just arbitrary. They can be anything. Okay. Now the next thing that a regular expression can be is plus of two regular expressions. So when can I prove that R1 plus R2 matches a string? Well, I can prove this when so I can prove it when R1 matches X's, and I can also prove it when R2 matches X's. So I'm going to have two proof rules here. I can say match this by left, where, and I have to prove as a sub-goal, prove match R1 X's. And then another one where I can say prove match R1 plus R2 X's by right, where prove match R2 X's. Okay. So the next case we have to deal with is times. So when does a string match times R1 times R2? Well, match R1 times R2 X's. Well, exactly when X's can be split into the concatenation of two strings, where the first matches R1 and the second matches R2. So I'm going to say by split, and then I'm going to have to give parameters of this proof rule saying what this split is. So I'm going to say by split y's z's, and then I'm going to have three sub-goals. One where I say that x's really does split into y's concatenate z's. And then two more, one for prove that R1 matches y's, and prove that R2 matches z's. Okay, now the only case we have left is star. This one is a little bit tricky. So I can always prove that star of anything matches the empty string no matter what. So I'm going to say prove match star R1 empty. I'm going to say by none. And then we need another rule. So there's more than one way to do this, but I'm going to say prove star R1 matches X's, where, and I'm going to say by sum. And then as a sub-goal, I need to prove that R1 times star R1 matches X's. So it turns out that this is a valid description of what it means for star to match a string. This is a sort of recursive definition because I can apply this sum rule any number of times to get R1 times R1 times R1 and so on, and then to stop I can say empty. Okay, so this is going to be my complete prop for matching. Yeah. Okay. So in the last video, I told you that about step indexing and how it's a good idea to have your props recursive on some piece of data. This isn't really like that, which means that you can do it, but it turns out to be extremely complicated with proofs that are multiple pages long. So instead, I'm going to show you this, which is a sort of demo version. You can't use this to prove some things that you would like to prove about regular expression matching, but you can prove some things. So here's the kind of thing we can prove. Say prove that if R1 times R2 times R3 matches some string, then I can change the bracketing and I still get a match. It still matches the same string. So the big picture here, or the bigger picture, is that regular expressions do form a monoid with times as the monoid operator and I, the regex I, as the neutral element, but the monoid equations aren't literally true as equations. They're true as equivalences that say that two regular expressions are equivalent if they match the same strings. So the equivalent of the rebracketing equation would be both this and the same implication, but the other way around. Okay, so let's prove this. So I'm going to say by imp I. So this is not a recursive proof, which is convenient because this prop doesn't really work for recursive proofs. I'm going to say by imp I, and now I'm going to say from my given. So ask knows that the only way that a times regex can match is if it was proven using the split rule. So when I send this, ask is going to give me a split. So I'm going to conveniently, I know how this proof is going to go, so I'm going to give these the strange names x's prime concatenate x's 3, because in the end we're going to split x's 3 ways into x's 1 plus x's 2 plus x's 3, and this thing is going to split further into 2 cases. So then I have to prove I get given this. R3 x is 3. Okay. Now I can use from again. I can say from this. And now I'm going to get another splitting of x's prime. So I'm going to say that x's prime is x's 1, concatenate x's 2, x's 1 matches R1, x's 2 matches R2. So now I've learned everything I can about my inputs. So now I'm going to start working on proving this. So I have to prove a times, something involving matching of a times regex. So I can only do that by the split rule. And I know that R1 matches X is 1, and this thing matches X is 2 concatenate X is 3. So I'm going to say I split X is 1, X is 2 concatenate X is 3. So now I'm going to get two sub-goals. One where I have to prove that X's really does split this way, and one where I have to prove this smaller match. And this one I can do again by the split rule, because I know that X is 2 concatenate X is 3 splits as X is 2 concatenate X is 3. So actually this by split should have 3 sub-goals, but Ask was able to solve all 3 of them automatically. Now the only place we have left to do work is in this sub-goal. Now, if I look at my givens, I know that X is X's prime concatenate X is 3, and X's prime is X is 1 concatenate X is 2. So I can make progress on this by changing the bracketing. And I've actually, up here, I've written the rebracketing rule for list concatenation as a helper proof here. So I'm going to make progress by saying by root of the other bracketing. Yeah. And then now I can prove this by under concatenate, I think. No. How do I do this? No, I know what I did wrong. This should be by root. I want to say X is 1 prime, X is prime concatenate X is 3, I think. No, I don't remember how I did this. Oh yeah, now I want to say by root X is prime concatenate X is 3. Yeah, and now I can say under concatenate. Okay, and there we go. Now it's proven. Okay. Whew. And that's it. This is the end of the course content. We've made it to the end. It's been a bit of a marathon. I'm planning to do one bonus video next week with an after credits scene, which will be optional and not on the test. Speaking of which, good luck on the test and courage.